Today we're going to talk about the area under a curve. I mean something like this. Here's my favorite example. Y equal x squared. Let's take the area from here to here. Just this much of it. How about this? All right. What is that area? Do you happen to know a formula for this? Probably not. You know, the formulas that you learn in geometry for finding the area of various things would include things like rectangles or triangles or circles, but that is none of them. It's vaguely triangular, but it has this curvy edge to it. How do you find the area of such a thing? It turns out there is a way to do this using antiderivatives, and it's pretty awesome. I thought maybe we'd have let's just do a little exercise here. I'm going to give you a little multiple choice here. What do you think that area is? I got A, B, C for answers, and D, I believe. Okay, 1, pi over 6, 1/3, or some number, 0.4073 something something something. What do you think? This is like, I don't actually expect you to know the answer. I'm just, think about it. What kind of a thing do you expect the answer to be? I'll give you a moment to think about it. Did you think about it? This question is like, what kind of a place do you think that this universe is? Is this universe a place where weird looking shapes like that have weird numbers for their area, or is this a place where weird-looking shapes like that actually have fairly simple numbers for their area? That would be kind of a magical place, right? I think those, answers A and C would be in that category. Answers B and D would be more like, you look at a weird shape, it's probably going to have a weird area. Actually, there is no, it turns out there is actually a good reason to rule out some of these answers. Here's a basic fact. Think about, what is the y value up here? If I consider like this box here, what's the area of that box? Well, since this is y equal x squared, this y value is 1 squared, which is 1. So actually this is the unit square. This box doesn't quite look like a square the way I drew it, but it is. It has area 1. So actually that immediately discounts answer A, right? Because the whole box is area 1. So certainly this little piece of it is not area 1, all right? Womp womp. How about pi over 6 actually is also discounted by this. That's because, consider this, not only is this whole box is 1, if you take a diagonal line right here, then actually this lower triangle is area 1/2. So whatever the area under that curve is, it must be less than 1/2. And actually pi over 6 is a little bit more than 1/2 because pi is a little bit more than 3. So when you divide by 6, you get a little bit more than 1/2. So it cannot be that. All right, we need an answer which is slightly less than 1/2. So actually C and D both are of that nature. Which one is correct? It turns out number C is the correct answer. All right, this shaded region here actually has area equal to 1/3. Slightly surprising. I don't know. When I first learned this fact, this was actually kind of mind-blowing to me. Just the fact that weird shapes can have non-weird areas. It's very. This is something that I did not expect as a young man learning about the world. Things turn out to be. This is a theme in mathematics. Actually, a lot of times things in mathematics turn out to be simpler than you thought they would be. This is one of the major sort of things that people identify as being beautiful about mathematics. The fact that there is structure and simplicity in mathematics where no one expects it. This is not, this area is not 1/3 just because some people wanted it to be 1/3, so we created it in order to be 1/3. But mathematics was created for other reasons, and it just turns out that this is 1/3, not because we wanted it to be, but just because it is for some magical reason. Anyway, it's a great thing about mathematics, and that's why I decided to become a mathematician. Not because of this, really, but just because of beauty in mathematics. I don't know if you care about any of that. Anyway, the fact that this has such a simple answer should suggest that there must actually be some sort of fairly simple method by which you can produce this answer. The way to find these areas, I said you can do this using antiderivatives. And it's not some kind of crazy big formula that you have to plug into and turn the crank. It turns out to be actually a very simple thing, which is why in this example you get a fairly simple answer. Now this is a fairly simple function too. So anyway, what we're going to talk about today is actually not finding the exact value of the area, but I want to talk about trying to estimate the area under the curve. Area under the curve of this nature, actually there's a special notation for this. How you write, there's some symbols that we use to indicate the area under the curve of x squared from 0 to 1, and it looks like this. We write this like an integral, like an antiderivative. The only difference between this and the antiderivative of x squared would be this little 0 and this little 1. That's when when you see this notation, that's how you tell I'm referring to the area under the curve. I'm not referring to the antiderivative. This is a number, right? It is the area. In fact, it is equal to 1/3 if you believe what I said before. The antiderivative is not a number. The antiderivative is a function with a plus c on it. This is a number. So this is called the definite integral. Remember I said before the antiderivative is something that's called the indefinite integral. This is actually the definite integral. On the surface at least, it seems completely different from the antiderivative. It should seem a little weird that we use the integral sign. It looks almost exactly like the antiderivative. That's because there actually is a relationship. But it means, so the definite integral, it means the area under the curve. All right. Now, I want to talk today about how could you estimate this value if you didn't already know the answer was 1/3. How could you try to get something close to the true answer of 1/3? All right, I'm going to draw the same picture again. I want to know, even if you don't know anything about finding area under the curve, which we don't, how could you try to guess, or how could you try to estimate the area under this curve? All right, I'm referring to this area right here. The issue, of course, is that this is a weird shape and you don't know how to find the area of a weird shape. The only shapes you know how to find the area of are things like rectangles, triangles, circles, maybe some other things, but certainly that list does not include a shape like this, which is like triangular, but it has a parabola on the top. Okay, what's a guy to do then if you don't know how to find the area? Here's a strategy. This is the strategy I'm going to use. I'm going to divide up this interval here between 0 and 1 is where I care about the area. I'm going to divide it up into a few little bits, maybe 4 pieces. And across each of these bits, I'm going to draw a rectangle that goes up and hits the curve on the right-hand side of each of these little intervals, like so. This one goes all the way up there. All right? And you don't have to be a genius to decide for yourself that the area of the rectangles is close to the area under the curve. By area of the rectangles, I mean if you took these 4 rectangles and added up their areas, that would be kind of close. I mean, maybe not exactly super close, but in this example, it would be kind of close to the area under the curve. Would it be more or less? Actually, it would be an overestimation in this case because of these bits here which stretch above the curve, right? But it would be an estimation to the true area under the curve. Actually, there's a name for this kind of way of computing the area or of estimating the area. So let's actually just do it. Add the rectangle areas. How would we do that? Rectangle areas are easy. You just multiply the base times the height. And actually, in this case, all the bases are the same, right? If I am going from 0 to 1 and I divide it into 4 pieces, the bases every time was 1/4, okay? Actually, in some notation that we're going to use for this, that 1/4, the width there, is what we're going to call delta x. This is called delta x, right? It's the width, and it's the same every time for all the intervals. What about the what about the heights of these rectangles? How do you find the heights of these rectangles? Well, let me just write down what these points are. This 0.25, 0.5, 0.75, right? For instance, what's the height of this rectangle here? Well, the height would be this high up. And how would you find that? Well, that happens to be the y value when x is 0.75. So actually the heights, they're not all the same, right? But the heights are the y values. And how do you get the y values? You plug these guys into the function. So you plug in. All right. So if I were to add these rectangles up, maybe I'll do it over here. We don't need this side of the picture. I'm going to say the area is approximately, this is an approximation to the true area. What I'm going to do is I'm going to add 4 things together, and each of those things is going to say 1/4 times some kind of a y value. So the first thing is 1/4 times, what's the first y value? It would be 0.25 squared. That's the y value when x is 0.25. You plug into the function. Why am I squaring? It's because the y value, in this case, y equals x squared. So 0.25 squared. So it's 1/4 times 0.25 squared. That was the first rectangle. The next one, 1/4 again. The height will always be 1/4 times how high is this rectangle? It will be 0.5 squared. Next one, 1/4. This rectangle, the height is 0.75 squared, whatever that is. And then the last one, 1/4 times this rectangle, the height is actually 1 squared, which is 1. But I'll write 1 squared just so it's clear where that came from. Okay, and that's that. You can plug all of this into your calculator if you want. Generally speaking, these types of problems, if you really want to see the answer as a single number, you're going to have to use a calculator. You could almost, well, I suppose you could simplify that by hand if you really wanted to. Anyway, I plugged this into my calculator. This is what I got, 0.46875. It's not a 5. Remember I said the actual area is 1/3, so that's, I suppose, kind of close. 1/3 is 0.33, etc., right? All right, that's the area, or that's an estimation of the area. Okay, what I just did, actually there's a name, a specific way of describing exactly this process here. Maybe I'll write it right up here. I don't want to erase all of this. So what I just did was estimate the area under the curve from x equals 0 to x equals 1. And that's this. Using, this is a standard way that you describe this, what I just did. N equals 4. That means you divide the thing into 4 rectangles. And the right endpoints, I mean right as opposed to left. When I drew the rectangles, I made them go up so that their height impacted the curve on the right endpoint. All right? N equals 4 and the right endpoints. Okay? This suggests, of course, that I could have chosen the left endpoints instead. Let's see what that looks like. All right, this time I'm going to do a similar thing, only these rectangles, when I draw them, they go up until they touch the curve on the left side. So the rectangle on this region, for instance, will be there. This one will be there. This one will be there. And this one actually will be sort of a stupid rectangle with 0 height because the left side of this interval is already touching the curve just at height y equals 0. Anyway, we can still add together these 4 rectangles, their areas. This one will be 0, but it still kind of counts as a rectangle. Let's add up the estimation of the area in that case. Again, we're going to multiply each time the width, the delta x, the base, I mean, times the height, which will be given by plugging in the left endpoint into the function. So we're going to get 1/4 times 0 squared. That's the first left endpoint. Then 1/4 times 0.25 squared. Then 1/4 times 0.5 squared. Then 1/4 times 0.75 squared. Right? Those are the 4 left endpoints, and they get plugged into the function. This also you can plug into your calculator if you really want to know what the answer is. And you get 0.21875. All right? No surprise, this is less than the true area, which is 1/3. That's because you can tell on the picture these rectangles are underestimating the true area. All right, 0.21875. Great. This is called the estimate the area with n equals 4 and the left endpoints. All right, I use the left endpoints rather than the right endpoints. Now, these estimations of the area are not terribly accurate. The true area is 1/3. That's kind of far off from 1/3, and the other answer that we used from the right endpoints was like 0.48 or something. That was also kind of far from 1/3. How could you make this estimation more accurate? It's a natural thing to do. If you were actually doing this in the real world, if it was your job to figure out the true area here by this method, this would probably not be a satisfactory answer. How could you make it more accurate? There is a simple way, and that is you increase the n. So more accurate, more with 2 R's, more accurate with higher n. All right, n, remember, refers to the number of rectangles. In this case, I used n equals 4. What would the picture look like if I used n equal 8? I'm going to do that with my orange marker. Check it out. Peep game on n equals 8. All right, instead of this rectangle, you would get this one, and then this one, right? And then here you get this one, and 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 again the stupid one. But you can see already, if you look just at the orange rectangles, maybe I should put that in there. If you look just at the orange rectangles, they are going to be more accurate in terms of estimating the area, because the regions of the true area that you miss out are smaller than they used to be, aren't they? Like this time, here's a region which I'm missing. My rectangles are going to be underestimating by that much. But in the blue version, I was missing the entire, this whole thing up there, right? So when you increase the n, the estimation of the area gets more accurate. So if you really wanted to do this and get a very accurate answer, you should just use a higher n. That's all there is to it. Let's try the same problem, but I want to actually do this computation using n equals 10. Actually, I didn't say and the right endpoints. How about that? All right. N equals 10. Before I did n equals 4. Now, first bit of advice, pro tip here. Don't bother drawing. Don't draw the graph and try to draw in 10 little rectangles. There's no point in doing that. You got to think about what is the important information which is included in my answer. Your answer consists of a bunch of things added together. In fact, there will be 10 of them. Each of those things will have the base width times the height. So the only thing you care about is what is the base width every time, and what is the height each time. The widths are all the same. The heights are going to be different each time. I think it is helpful. So it's not helpful to try and draw the graph with the little rectangles. I think it is helpful to draw a little chart of the interval that you're considering. So from 0 to 1, I'm going to make a little chart here. And n equals 10 means I divide this into 10 bits. It is helpful to make a little diagram like this. Maybe you don't have to actually write in all those numbers if you think that's annoying. And I'm choosing the right endpoint. So on my diagram, I'm just going to circle the right endpoints. These are the 10 points which I'm going to plug into the function. All right. So what is my answer? The area is approximately, what you're going to see here is a sum of 10 things. Each thing consists of the width times one of these points plugged into the function. And that's really all there is to it. Maybe we should say also, what is the delta x here? The width of each of these little bits? I think it's obvious once you make your little chart here. It's 0.1, right? What am I going to do here? Like I said before, every term consists of 0.1 times the height, which is one of these numbers, squared. So I go 0.1 times 0.1 squared plus 0.1 times 0.2 squared plus 0.1 times 0.3 squared plus, it's about this time that you get tired of writing all of this stuff, which is totally fine with me. Put a little dot, dot, dot. It is important though, if you're going to put the dots, make sure you tell me where it stops. Where does it end? It ends here. 0.1 times 1 squared. That's the last one. All right. If you want to write the dots on your homework or on your tests or whatever, that's totally fine with me. Just make sure you tell me where it stops and put enough stuff at the beginning so that I know that you know what the pattern is. All right. This, if you care, you could plug this into your calculator. I did this and I got 0.385. Come on. I have a problem writing fives. 0.385. This is a much better estimate of the true area, which, remember, just because I said so, the true area is 1/3. So that's actually getting pretty close. Let's do the same thing using the left endpoints. This is usually annoying when someone asks you to do a problem and then says, "Okay, now do the same thing again, but change it." It's actually almost completely the same. What's the difference? And the difference is in your chart here, instead of using those ones which are circled, use the ones on the left. So maybe I'll just so it's clear. 9, 10. This time around, instead of using the points on the right, I circle the points on the left. Right? No pun intended. Right on the left. So this time the answer is area is approximately, it's still going to be 0.1 times a bunch of stuff where you plug the numbers into the squaring, but this time around the numbers which I plug in start with 0 and they end with 0.9. So I will not include, I will include 0, but I will not include 1, and that's the only difference. So 0.1 times 0 squared plus 0.1 times 0.1 squared plus 0.1 times 0.2 squared, etc., finishing at 0.1 times 0.9 squared. This is why it's especially important that you tell me where it stops, because it actually is different. All right, that's the only difference. So you get basically the same stuff. It's just that the one on the right includes the one on the right, the one on the left includes the one on the left. That's all there is to it. And what is this? If you plug that whole thing into your calculator, you will see the answer is 0.285. How do you like that? All right. This is an underestimation. The true value, remember, is 0.33 repeating. But these are quite a bit closer to the true answer than the estimations that we had before. Let's just talk a little bit abstractly about what we've been doing here. That area estimation always looks something like this. It's a sum. And inside of the sum, what you see is this delta x thing. Remember, that's the width of each subdivision. And then you multiply that by some number being plugged into the function, where this xi represents, the sum is across the i's. The xi represents something like I equals 1 to n. There's n different subdivisions, and you add them all up where you're plugging into the function each time. This is a formula that you could write down for the estimation of the area. I'm not being specific whether I mean left or right. They both end up being n different points added in and summed up like that. All right. Actually, if you write it, if you just flip those around, you will see what this antiderivative, or the definite integral, this is actually this is sort of where the integral sign comes from. It comes from the idea that the integral, that is the area under the curve, the true area under the curve, is fairly close to a sum if you were to add together values of the function each time multiplying by delta x. Where this comes from is this delta x sort of became written as dx, and then this summation was turned into this weird looking s. Actually, that's why the integral sign looks like an s. It's meant to be some sort of reference to the fact that this comes from the sum of something. This is approximated by the sum of something. And in fact, they are equal if you do something like this. Actually is equal to the limit as n goes to infinity of something like this, where the n is up here, right? Sum I equal 1 to n f of xi delta x. All right. So once again, this, if you like, you could say this is the true definition of the definite integral. This is how you would actually find the true answer of the area under the curve. It turns out this definition over here, just remember, we had the derivative had a definition in terms of a limit. Limit as h goes to 0, f of x plus h minus f of x divided by h. Remember that thing? That's the thing that is very hard to use directly. Once you learn some tricks, you basically abandon that formula forever. it's a similar thing with the antiderivative. This formula right here is actually very hard to use directly. We're going to use some tricks which will allow us to essentially never have to do this formula over here. But it's good to know that there is such a formula. Let's just try a couple more examples of this estimations, and that'll do it for us. Alright, I just want to do one example, and that should do us. Estimate the area under the curve f of x equal e to the x minus 1 from x equal 1 to x equal 3 using n equal 4 and part A, the left endpoints, part B, the right endpoints, part C, the midpoints. We didn't even talk about the midpoints. A and B are very similar to each other, and it turns out C is also fairly similar. Let's see if we can do it. I hope you're not worried about this e to the x thing. It turns out not to be really an issue at all. It almost doesn't matter at all what this function is. These problems do not get harder if it's a more complicated function. Anyway, let's do it. I'm going to begin by drawing my little chart of the interval that we're concerned with. We're going from 1 to 3 using n equals 4, so you got to split it into 4 sub-intervals. Let's try to label these points. You can usually label these points just by by common sense, right? Straight up in between 1 and 3 is 2, and then in between 1 and 2 is 1.5, and then this will be 2.5. So what is the delta x here? The width of each of these little subintervals is 0.5, right? In fact, actually, so this you can figure out just like with basic common sense. But actually, there's a formula for the delta x. If for whatever reason the endpoints are weird or something, you need to, and it's hard to figure out what the delta x is. This is worth remembering. Here's a little formula: b minus a over n, where b and a are the two endpoints, the 1 and the 3 in this case. Where this comes from is just b minus a is the total width of the interval, and then you divide by n because you're chopping it into n pieces, and so the result will be the width of each of the little n pieces. So if you were to use that in this case, if for whatever reason you can't figure out how to draw the picture, it would have been 3 minus 1 divided by 4, which is 2 over 4, which is 1/2, right? Great. Anyway, for the part A, I'm using the left endpoints. That would be here, 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 and here. And you're basically ready at this point to write down your answer. You say the area on the left side, using the left endpoint, so this is my answer to part A, is... each time I'm going to add up, multiply by 0.5. So I'm actually going to do this in 2 steps. 0.5 times f of 1 plus 0.5 times f of 1.5. 0.5 times f of 2 plus 0.5 times f of 2.5. Right? I just plugged in the left endpoints to the function. And now what is f of 1, f of 1.5, etc.? You just plug in here, all right? 0.5 times e to the 1 minus 1. Plus 0.5 times e to the 1.5 minus 1, plus 0.5 times e to the 2 minus 1, and 0.5 e to the 2.5 minus 1. Remember your parentheses there. All right, and that's all there is to it. Do you believe me now when I said it doesn't really matter what the function is? Because you don't have to take the derivative or antiderivative or anything. You don't really have to do anything to this function. You just plug into it, and you just leave. That's the answer, right? If you want to plug that into your calculator, you can. If you don't have a calculator, that's the answer. This is a number, right? And did I do this on my paper? I don't think so. It doesn't matter. I don't really care what that is as a number. That is the answer, though. All right, that was the left endpoints. Let's do it with the right endpoints. All right, since I've already done this one, it's not hard at all to say what's the difference between this, which was the left endpoints, and the right endpoints. The difference is in the right endpoints, you do not use the first point, which is the 1, but you do use the last point, which is the 3. So I don't think it's necessary to really make a big deal out of showing your work. You already did the whole thing in the first place. It's the same, only I start here and I go up to 3. So it's 0.5 e to the 1.5 minus 1 plus 0.5 e to the 2 minus 1 plus 0.5 e to the 2.5 minus 1 plus 0.5 e to the 3 minus 1, and that's my answer for part B. All right? I hope you will find these are actually pretty easy problems to do. You just sort of plug everything in, you make your little chart, and it all works out great. Okay, part C, the midpoints. We didn't even talk about the midpoints. It's not much harder, though. The difference with the midpoints is... actually, you use the same delta x. When you make your little chart here from 1 to 3, you still should figure out where these points are, and they are where I said they are. Only this time, instead of circling the left points or circling the right points, you circle the midpoints of each interval, which would be here, 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 and here. These are the midpoints. What actually are those points? Well, again, you can just figure them out by common sense. This is 1.25, 1.75, 2.25, and 2.75, right? In each case, they would be just the average of the two numbers, or the midpoint of each interval, all right? But anyway, you use the same formula again. You just use these midpoints to plug into it. So my answer for part C is 0.5 e to the 1.25 minus 1 plus 0.5 e to the 1.75 minus 1 plus 0.5. E to the 2.25 minus 1. Oh, minus 1. 0.5 e to the 2.75 minus 1. That's how we do it.